Okay, so let's move on to discuss what it is that neurons actually do. We'll start by discussing what's happening while the neuron is at rest, or being inhibited. This is referred to as the resting potential. The neuron is at rest, but it still has the potential to fire. So what is it that neurons do? Well, here's our working definition. The function of a neuron is to take in information from the environment or from other neurons, integrate that information, and then send the information along to other neurons. That's really not clear, so let's explicate a little. Our definition says that the neuron takes in information from the environment or other neurons. Let's leave out the environment for now. We'll cover that in the next part of this unit. Let's just focus on neuron-to-neuron transmission. We also need to deal with this word information. Let's take that out and replace it with chemical messengers. These chemical messengers are neurotransmitters such as dopamine, serotonin, or GABA. And then there's the word integrate. Well, that simply means to put together. For example, both the excitatory and inhibitory chemical messages. So here's what we end up with. The function of a neuron is to take in the chemical messages that other neurons send it, add together the excitatory and inhibitory ions, and pass on chemical messengers to other neurons if the excitation is great enough. So how does all that happen? Well, first we have to go back to 5th grade math and positive and negative numbers. So let's say that you're the treasurer of an organization, and to aid your bookkeeping, you keep a cash box. And in that box are two types of paper slips. Some represent debits and are thus negative numbers. Others represent deposits and are positive numbers. Figure 1 here shows the contents of your treasury box with a net value of negative $5. So let's say a potential donor has said that if your club can get up to a positive $5 mark, then she will provide a gift of $1,000. So adding in deposit slips that are positive, like $2 more, nudges you towards your threshold value of positive 5. Taking out or adding debit slips or subtracting a deposit slip pushes you away from that threshold. So let's take that concept and apply it to the neuron. The box represents a neuron, which is a living cell. The debit slips represent molecules within the neuron that carry the negative electrical charge. In real neurons, these negatively charged ions are mostly large protein molecules that cannot move out of the neuron. So we'll use the symbol negative P to refer to these. So we have these negative proteins throughout the neuron. I think we'll probably have to zoom in here a little bit. So the deposit slips represent positively charged ions, which can be either potassium or sodium. Potassium ions, we'll abbreviate as positive K, are concentrated on the inside of the neurons. Sodium ions, on the other hand, positive Na, are concentrated outside of the neurons. Also concentrated on the outside of the neurons are negatively charged chloride ions. So although the negative protein ions always stay inside the neuron, the other three ions can pass through the cell wall or the cell membrane. This is analogous to the treasury box in adding and subtracting these ions will influence the net value or the potential within the cell. And as with the treasury box, if that potential becomes positive enough and the threshold value is met, then a major event occurs. So this delicate balance of these four ions creates what is called the resting potential inside the neuron. This means that when no information, no excitatory or inhibitory chemical messengers are present, then the four ions are in equilibrium. Our negative proteins are inside the neuron and stay there. They cannot pass through the membrane. The positive potassium ions are inside the neuron and can pass through the membrane to the outside. The positive sodium ions are outside of the neuron and can pass through to enter the cell, and the negative chloride ions are also concentrated on the outside and also can pass through the membrane into the cell. We really should call this dynamic equilibrium because the three major forces at work here produce the delicate balance. The first force is electrostatic pressure and can best be described as opposites attract, meaning that areas of negative charge, like the negative 70 millivolt charge inside the neuron, attract positively charged ions like sodium. Conversely, charges that are alike will repel each other, so the negative 70 millivolt charge inside the neuron will repel negatively charged ions like the chloride. The second force of this dynamic equilibrium is the tendency for molecules to move from areas of high concentration to areas of low concentration, sometimes referred to as the concentration gradient. Therefore, since the chloride ions are concentrated outside of the neuron, they will tend to move into the cell where there are fewer chloride ions. And then the third factor is the permeability, the ability of ions to pass through the cell membrane. So if we look at this model, we can consider these three forces and how they act on each type of ion. Notice first that the cell membrane of the neuron is drawn as a broken line. This is to represent the concept of permeability, that is, that ions can pass through the membrane. So chloride is concentrated outside of the neuron, so they will tend to move through the membrane into the cell. However, the negative chloride ions are negatively charged, so the negative charge inside the neuron will repel them. In fact, these two forces exactly balance each other out such that the chloride ions do not cross the cell membrane while the neuron is at resting potential. Similarly, the two forces act in opposite directions for potassium. It tends to move out of the neuron because it is concentrated inside. But the negative charge inside tends to attract these positive ions. For potassium, the concentration force is a little bit stronger than the electrostatic force, and therefore some potassium ions leak from the neuron when it is at resting potential. Notice now the sodium ions. We can see that both forces are attracting or acting on the sodium ions to push them into the neuron. So why then is our negative 70 millivolt electrical potential not quickly drained? Well, the answer is that the permeability of the membrane at rest is very low for the sodium ions, while it's relatively high for the potassium and for the chloride. In other words, the sodium ions cannot get into the cell as easily as the potassium ions can get out, thus giving us a slightly negative charge. Permeability does not mean just that the cell membrane has holes in it. Rather, it means that embedded within the cell membrane are channels that are specific to each type of ion. These are called passive channels, and the ions can pass freely through them. But each channel allows only one type of ion to pass. There are a lot of passive channels for potassium, but there are very few for sodium. Therefore, the net force pushes the potassium ions out of the many channels, while only a small number of passive channels allows the sodium in. This is despite the very strong force trying to push the sodium into the cell. This is where the third force that helps maintain resting potential comes into play. This third force is the sodium-potassium pump, and it does exactly that. This little mechanism, which is a protein, a negatively charged protein, pumps those escaping potassium ions back into the neuron, and it pushes out the few sodium ions that have managed to get through those passive channels, pushing them back out. This maintains the neuron at a resting potential charge of about negative 70 millivolts. So in the next presentation, we'll discuss the excitatory and inhibitory processes, and then we'll talk about action potential and the actual firing of the neuron.